Welcome back. In this video, we are going to solve problem 4-101 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Materials by R.C. Hibbeler. So statement is the rigid lever arm is supported by two A36 steel wires having the same diameter of 4 mm. If force of 3 kN is applied to the handle, determine the force developed in both wire and their corresponding elongation. Consider A36 steel as an elastic, perfectly plastic material. So you can see this is the handle where there is a 3 kN load applied, and these are two steel wires of 4 mm diameter. So you have to find the forces in this wire as well as elongation. Now you can see due to this force there will be elongation in wire A, B and CD. So what we will do is that first step is that we will find these forces. So this handle tends to increase the length of this wire AB. As a result, this wire AB applied force that will act downward. So this, if we remove this force, this wire AB will exert a force downward. That this force is FAB. Similarly, if you remove this wire CD, so this will also exert a vertical force FCD in downward direction. And this at point E there is a pin support. So as a result of this, if you remove this support, so there will be a horizontal reaction force which is equal to EX, and there will be a vertical reaction force which is represented as EY. Now we'll find this FA, B and FCD by using equation of equilibrium. So what are these equation of equilibrium? So first equation of equilibrium is that sum of all moments about point E is equal to 0, taking the counterclockwise movement as positive. So about point E, these two forces are passing through point E, so they are not producing movement. So only the movement which is producing the only forces which is producing movement about point E is the first one is this P, and perpendicular distance is 450, and this is producing clockwise movement, so it will be negative. So I will write P, which is 3 kN, so 3000 multiplied by 450, and this is producing counterclockwise movement, so it is negative. The second movement is due to FCD, and perpendicular distance is this 150, and since this is producing counterclockwise movement, so it will be positive. So I will write plus FCD into 150, and the last force which is producing movement about point E is FAB into perpendicular distance is 300, and this is also producing counterclockwise, so it will be positive. So I will write plus FAB into 300 is equal to the sum of all moments about point E will be equal to 0. So if you divide this equation by 150 on both sides, so you will get 2 times FAB plus FCD is equal to 9000. This is your equation number 1. Now we can see that due to this load of P, this wire AB and CD elongates. So as a result, this point AB comes toward this will be new point A dash, and C will come toward this point, and let this point is C dash. So this change in length between A and A dash is del A change in length of AB, and from A to C it is this one, del CD. Okay, so this will be a straight line at this point. Let me draw it again. It will be a straight line because we assume that this is linear elastically perfectly plastic material. So this is your point C. Okay, now what we will do is that we will perform another analysis, that is elastic analysis. Let me write it, elastic analysis, and we have assumed that these material wires are elastic perfectly plastic material. So you can see that there are two similar triangle. One is this one, clear, and another one is this one. So if we take the ratio of their side, for example, if I take change in length of AB divided by this total length, which is equal to 300 millimeter. So it will be del AB divided by 300 will be equal to del CD divided by 150. So from here, what I will get is that del AB, change in length of wire AB, will be equal to 300 divided by 150 multiplied by change in length of CD. And if you further simplify it, change in length of AB will be equal to 2 times change in length of CD. Now we know that change in length is equal to force FAB into length AB divided by A into E. Since area is same, because both have same diameter, so area will be same, and 2 multiplied by change in length of CD will be equal to FCD into LCD divided by A into E. So again, if you further simplify it, this A will cancel with this A, and material is same, A36 steel, so and length are also same, so these will cancel. So we will get this FAB is equal to 2 times FCD. So this will be our equation number 2. Okay. Now what we are going to do is that we will find the normal stress in each wires. So how we'll find that? Let me write it, normal stresses. But before normal stresses, what I will do is that if I solve this equation 1 and 2, solving equation 1 and 2 simultaneously, so you can also put equation number 2 in equation number 1. So let's put it, FAB is 2 times FCD, so 2 multiplied by 2 FCD plus FCD is equal to 9000. So when you solve this, you will get force in wire CD will be equal to 1800 Newton. So if you have this FCD, so put FCD in equation number 2. So you will get FAB is equal to 2 times FCD. So 2 multiplied by 1800 Newton will give you FAB. That will be equal to 3600 Newton. So these are the two forces in wire AB and CD. Now we will check stress in these wires. So normal stress in wire CD will be equal to FCD divided by area of CD. So FCD is 1800. The diameter of wire is given 4 millimeters. So area will be pi by 4. And 4 millimeter in meter is 0.004 pi by 4 d square. So when you solve this, this will be equal to 143.24 megapascal. Since we are given the A36 material steel, so from property table, its value is 250 megapascal. So you can see that stress in CD is less than yield stress. This is 143.24 megapascal, which is less than 250 megapascal. So it means that the stress or force in wire is okay. Now we will find the stress in wire AB. So stress in wire AB is equal to force in AB divided by area of AB. So force is 3600 divided by area is pi by 4. Again, diameter is 0.004 square. So when you solve this, you will get stress will be equal to 286.48 megapascal. And you can see this is greater than yield stress, which is 250 megapascal. So it means that this is not good. So what we will do, why not good? Because it is given that material behave elastically, perfectly plastic, and it is exceeding the yield stress. So what we do is that I will write it, since wire AB yields, so the elastic analysis is not valid, and the solution must be reworked. So how you will rework? So we will use that, we know that yield stress is equal to force into area. So from here, this force in AB will be equal to, we will calculate force based on yield stress so that it lies within the yielding range. So we will know that yield stress into this area of AB will give force. So yield stress is 250 megapascal. So 250 into 10 raised to the power 6 multiplied by area is pi by 4. Diameter is 0.004 square. So when you solve this, you will get FAB, and FAB will be 314.159 Newton, or you can say that this FAB will be equal to 3.14 kilo Newton. Now you have this force clear, and what we will do is that we will put FAB is equal to 3.14 kilo Newton in equation 1 or 2. So if I put it in equation number 2, so I will also get FCD will be equal to 2.72 kilo Newton. Now again we will check the stresses. Clear? So for that, I will calculate CD is equal to FCD divided by area of CD. So FCD, which was new calculated, was 2.72 kilonewton. So 2.72 into 10 raised to the power 3 divided by pi by 4 into 0.004 square. So when you solve this, you will get 216.20 megapascal. And now you can see this is less than yield stress, which is 250 megapascal. So it means that it is still okay. So answers that force in wire AB is equal to, and force in wire CD is equal to. So force in wire CD is 2.72 kilonewton, and force in wire AB is 3.14 kilonewton. So this is the answer of our first part. Now moving toward next part, that is determine the elongation. Determine elongation in both wire AB and CD. So how you will find this? We know that elongation, change in length of CD, is equal to FCD into LCD divided by A into E. So FCD is 2.72 into 10 raised to the power 3 multiplied by length of each wire is given as 300 millimeter. So I will multiply it with 0.3 meter divided by area, which is pi by 4 into 0.004 square multiplied by E, which is 200 gigapascal. You can check the property, 200 into 10 raised to the power 9. When you solve this, it will give you 0.0000324 meter. Or you can say change in length of wire CD will be equal to 0.324 millimeter. Now we'll find change in length of AB. So change in length of AB is equal to FAB into LAB divided by area of AB into E. Put the values FAB is 3.14 into 10 raised to power 3 Newton. Length is same, which is 0.300 divided by same diameter because the diameter is same area because the diameter is same and same material. So modulus of elasticity is 200 gigapascal, which is 200 into 10 raised to power 9. So when you solve this, you will get 0.000649 meter, or you can say change in length of AB is equal to 0.649 millimeter. Also, you can solve this by using this equation as well. Let me show the equation here. This is the equation. You can also calculate it if you know delta CD. So we can also calculate delta AB is equal to 2 times delta CD. So 2 multiplied by delta CD is 0.324. So it will be again equal to 0.649 millimeter. So change in length of wire AB is equal to 0.649 millimeter and change in length of CD is 0.324 millimeter. And these are the answers of our second part. So this was all about this problem 4-101. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-102 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the rigid lever arm is supported by two A36 steel wires having the same diameter of 4 millimeter. Determine the smallest force P that will cause only one wire to yield, and in B part, both wires to yield. Consider A36 steel as an elastic, perfectly plastic material. So you can see this is a handle where P load is applied and there is wire AB and CD. At point E, there is a pin support. So you have to find this force P which will cause one of the wire to yield, and in P part, both wires to yield first. The material is A36, so I have written the given data. The rigid lever is supported by A36 steel wires, and the yield stress of these wires is 250 megapascal. That is taken from mechanical property of the table, and E is also taken 200 gigapascal. Diameter of both wires are same, which is 4 millimeter or 0.004. So you have to find the P for one wire to yield and both wire to yield. So let's start with the solution. Now you can see due to this load, there will be elongation in wire AB and CD. As a result, if you remove this wire, so the wire exert downward force on this handle. So we will find this. So that if you remove this wire AB, so there will be a reaction force of this wire which is FAB on the handle. Similarly, if you remove this wire CD, so there will be a vertical reaction force FCD which will be acting downward. And if you remove this pin support, so there will be horizontal reaction force which is EX, as well as vertical reaction force which will be equal to EY. So we will find this FAB and FCD by using equation of equilibrium. So the equation is sum of all moments about point E is equal to 0, and taking the counterclockwise moment as positive. So about point E, the first moment will be due to this force, and perpendicular distance is 300, clear, and this is producing counterclockwise, so it will be positive. So I will write FAB into 300. The second moment is due to this FCD, and perpendicular distance is 150, and this is also producing counterclockwise, so it will be positive. So I will write plus FCD into 150. Clear. And the last force which is producing moment is this force, and perpendicular distance is 450, and it is producing clockwise moment, so it will be negative. So I will write minus P times 450 is equal to 0. These two forces are passing through this point E, so they are not producing any moment. That's why I haven't taken this. So if you divide this equation by 150 on both sides to simplify it, so we will get 2 times FAB plus FCD is equal to 3P. Let this is your equation number 1. Now you can see due to this load, there will be elongation in wire AB and CD. So as a result, point A will let point A move toward this, clear, and point E is fixed, so it will be like this. So point C, this is new point of A dash, and this is C dash. So this distance between A and A dash is change in length of AB, and distance between C to C dash is change in length of CD. And you can see we get a triangle. Clear. Now here we have two right angle triangle. One is this one, and the second triangle is this one. These are similar triangle. So we will apply elastic analysis. I will write it elastic analysis in order to find the relationship between these two change in length. So by using similar triangle, if I take the side del AB divide by, initially I will take this larger triangle. So AB divided by this length, which is 300, will be equal to, now if I will take smallest triangle. So this CD, del CD divided by this length, which is 150. So del CD divided by 150. So from here, I will get change in length of AB is equal to 300 divided by 150 into change of length of CD. So again, it will give us change in length of AB is equal to 2 times change in length of CD. This is your another equation. Now, if I further simplify it, change in length of AB is equal to 2 times change in length of CD. So change in length of AB will be equal to FAB into length of AB divided by area of AB into E is equal to 2 multiplied by FCD into LCD divided by ACD into E. Clear? Since both diameters are same, so area of EB is equal to area of CD will be equal to A, and length are also same. LAB is equal to length of CD is equal to L, which is equal to 300. So this will cancel with this, E and E will cancel because material is same and this are same. So we will get FAB is equal to 2 times FCD. And this is your equation number 2. Now what we will do is that our first part is that assume one wire to yield and yield. So we will assume that wire AB will yield. Why? Because in previous problem we have seen that wire AB yields. So this force in AB will be equal to yield stress multiplied by area of AB. Yield stress is 250 megapascal, so 250 into 10 to the power 3 multiplied by area pi by 4, diameter is 0.004 square. So from here, when you calculate it, you will get force in AB will be equal to 3141.59 Newton. So this is the value of force in wire AB. So put this FAB in equation number 2, which is this one. So FCD will be equal to FAB divided by 2. So 3141.59 divided by 2 will give you 1570.80 Newton. So I will get FCD is equal to 1570.80 Newton. Now you have the value of FAB and FCD. So what we will do is that put FAB and FCD in equation number 1, which is this one. Clear? So when you put it 2 times FAB, which is 3141.59 plus FCD is 1570.80 is equal to 3P. And when you solve this, you will get P will be equal to 2618 Newton. Or you can say P will be in term of kilonewton, it will be 2.62 kilonewton, which is the answer of our first part. Now we will move towards second part, that both wire yield. So again, I will move toward the next page. So as this will fail, so we'll move that plastic analysis here. And we will write, since both wires AB and CD are required to yield, therefore force in AB is equal to force in CD, and that will be equal to yield stress of steel multiplied by the area. So 250 is the value of yield stress multiplied by the area is pi by 4 d square, and d 0.004 square. So when you solve this, you will get the value of forces in both wire will be 3141.59 Newton. This will be equal to FAB and equal to FCD. Now put FAB and FCD in equation number 1, which is again this equation. This is the equation. 2 times FAB plus FCD is equal to 3 times P. So P will be equal to 2 by 3 to P will be equal to 2 by 3 times FAB plus 1 by 3 times FCD. So put the value 2 by 3, 3141.59 plus 1 by 3 times 3141.59. And when you solve this, you will get this P will be equal to 3141.59 Newton, or in kilonewton it will be 3.14 kilonewton, which is the answer of our second part. For both wire to be yield, P should be equal to 3.14, while in first part P should be equal to 2.62 kilonewton for one wire to yield. And that was all about this problem 4-102. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then hit the bell icon and subscribe my channel as well. So that was all about today's. I hope you have enjoyed. Kindly share my channel with your friends and help me in growing my channel further. Thank you for watching. Welcome back. Problem 4-99. This problem is taken from chapter number 4, Axial Loading, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the rigid beam is supported by a pin at A and two steel wires having diameter of 4 mm. If yield stress for the wire is 530 megapascal and modulus of plasticity for steel wire is 200 megapascal, determine the intensity of distributed load W that can be placed on the beam and will cause wire EB to yield. What is the displacement of point G for this case? For the calculation, assume the steel is elastic and perfectly plastic. So you can see this is the beam at point A, it is pin supported, and at point B and C there are two steel wires of 4 mm diameter that is supporting. There is a distributed load over whole length which is W. So you have to find this W as well as displacement of this point G due to this load. So you have to find this displacement. So let's start with the solution. So what will be the first step? The first step is that if you remove this pin support at point A, so you will be having a reaction force which is equal to RAY, and if you remove it, so there will be horizontal reaction force RAX. Similarly, if you remove this wire BE, so there will be a vertical reaction of this wire EB on this beam, which is FEB. And similarly for CD, the vertical reaction force offered by this wire CD will be equal to FCD on the beam. So what we will do is that, again, you can see there is a distributed load. So this distributed load, when converted into a point load, so it will be equal to W, the magnitude, into the length over which it acts. So 400 plus 250 plus 180 is 800 millimeters. So 800 millimeter is 0.8 meter. And the unit will be in Newton per meter. Okay. So what we will do is that we will apply equation of equilibrium, that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So you can see moment about point A, the first moment is due to this FEB, and perpendicular distance is this 0.4 meter, and this is producing counterclockwise, so it will be positive. So I will write FEB or FBE into 0.4. The second moment is due to this FCD, and perpendicular distance is now 0.65 meter, and this is also producing counterclockwise, so it will be positive. So I will write plus FCD into 0.65. And the last moment that is produced due to this W into 0.8, and perpendicular distance is 0.4, and this is producing clockwise, so it will be negative. So I will write minus 0.8 times W into the perpendicular distance is 0.4. So from here, what we will get is that 0.4 times FBE plus 0.65 times FCD is equal to 0.32 W. That this is your equation number 1. Now we cannot apply any other equilibrium equation because it will not give you our required answer. So what we will do is that we will perform plastic analysis of wires, steel wires. What do you mean by plastic analysis? That the force is producing yield, the force is yield stress, and it is deforming permanently. So what we will assume that both steel wires fail. Both steel wires. Okay, let me correct it. This is steel wires yields. Yields mean it is deforming permanently. So for that we have been given the yield stress is 350 megapascal. So yield is 350 megapascal, and we know that yield stress is equal to yield force divided by area. So for BE and CD steel wire, the yield forces will be F of BE is equal to F of CD, because both have the same diameter. We will have this formula sigma y into its area. So you have sigma y, which is 350 megapascal. So 530. Sorry, this is not 350, this is 530. Correct it as well. 530. So 530 into 10 raised to power 6 multiplied by area. Diameter is given as 4 millimeter or 0.04 meter. So it will be pi by 4 times 0.004 square. That will give you force in BE and force in CD. So when you calculate it, both these forces, FBE is equal to FCD, will be equal to 6.660 kilo Newton. Now you have these forces, that this is your equation number 2. So put value of FBE and FCD in equation number 1. So this is your equation number 1. You can see this is your equation number 1. So when you put it the value, so you will get this W. I am not going to put it because this is very easy step. So you will get 21.9 into 10 raised to power 3 Newton per meter. Or you can also convert it is equal to 29.1 kilonewton per meter. Now you have this value. So what we are going to do is that we will find the displacement of this point B. Clear? So how we will find this displacement? So let's see that. Let me write first displacement. So as wire EB or BE achieve yield stress. So corresponding yield strain will be this one, and we know that this will be equal to yield stress over modulus of elasticity. So you can just put the value yield strain is equal to 530 into 10 to the power 6 divided by modulus of elasticity is given as 200 gigapascal. So 200 into 10 to the power 9. So when you solve this, you will get this yield strain will be equal to 0.002650 millimeter per millimeter. Now we have this yield strain. So what we are going to do is that we will find the change in length of this wire BE. So we know that strain is equal to change in length or original length. So for BE wire, clear? So this yield strain in wire EB or BE will be equal to change in length of BE divided by original length of BE. Clear? So we will find change in length of BE, that will be equal to LBE multiplied by yield strain. So what is the length of BE? So let me check. You can see both have length of 800 millimeter, which is equal to 0.8. So 0.8 multiplied by yield strain, which is 0.002650. So when you solve this, you will get change in length of wire BE will be equal to 2.120 millimeter. Now we have these values. So again, you can see that initially this beam was like this, clear? And due to the loading, this is your point A, this is your point, let's say B, this was your point C, and this is your point G. So due to the loading, the beam will go like this. So this will be the change in length of BE, delta BE. This will be change in length of delta CD, and this will be the change in length of our delta G, displacement of point G. So we know that the distance between A and B was 400 millimeter, or which is 0.4 meter. This distance between B and C was 0.25 meter, and distance from C to G is 0.15 meter. Now what we'll do is that you can see you have two similar triangles, three similar. One is this one, clear? The second one is this one, clear? So we will take this similar triangle. Let's say this is your 1 and this is your 2. So two similar triangle. The first one is triangle, right angle triangle AB1, and other is triangle AG2. So by taking the ratio of their sides, so if I take AG divided by G2, so if AG divided by G2, that will be equal to AB divided by B1. So what we will get is that AG is totally 0.8, clear? So 0.8 divided by delta G, G2 is delta G, that will be equal to 0.4 divided by delta BE, clear? So from here we will get delta G will be equal to 0.8 divided by 0.4 into delta BE, that is equal to 2 times delta BE. Now what we get is that delta G is equal to 2 times delta BE. So put the value 2 multiplied by delta B is 2.120 millimeter. So you will get delta G will be equal to 4.24 millimeter, and which is the answer of our this question. So this was all about problem 4-99, in which we have been asked to find the distributed load, clear, as well as the displacement of point G. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos and help me in growing further. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-100 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the rigid beam is supported by pin at A and 2 steel wires, each wire having diameter of 4 millimeter. If yield stress for the wire is 530 megapascal and modulus of elasticity of steel is 200 megapascal, determine. The first part is intensity of distributed load W that can be placed on the beam that will cause only one of the wire to start yield. And in B part, smallest intensity of distributed load that will cause both wire to yield. For the calculation, assume that steel is elastic, perfectly plastic. So you can see this is the beam, clear? There is a pin support at point A, and at point B and C there are two steel wires of having diameter 4 millimeter, and there is a distributed load acting on over the whole length, which is W. So you have to find this W for one of the wire to yield, and then in second part we have to determine this W for both wires to yield. So let's start with the solution. So first step is that if you remove this pin support at point A, so you will be having a vertical reaction force, and this will be RAY, as well as there is a horizontal reaction force which will be equal to RAF. X. And similarly, if you remove this wire BE, so there will be a vertical reaction offered by this wire EB or BE on the beam. And same is the case for wire CD, that it will act a vertical reaction force on beam, which is equal to FCD. And there is a distributed load of magnitude W. So when this distributed load is converted into a point load, so it will act at the middle of this beam, and the magnitude will be W into the length. And length is 400 plus 250 plus 150 is 800 millimeter, which will be equal to 0.8 meter. And its unit will be Newton per meter. Clear? Now we'll find this FBE and FCD by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, the first moment will be FBE, and perpendicular distance is 400, which is 0.4 meter, and it is producing counterclockwise, so it will be positive. So I will write FBE multiplied by 0.4. The second moment that is produced due to FCD and perpendicular distance is 0.65 meter, and it is also producing counterclockwise movement, so it will be positive. So I will write plus 0.65 times FCD. And the last moment that is produced due to this load and perpendicular distance is 0.4 meter, and this is producing clockwise, so it will be negative. So I will write minus 0.8 W times 0.4 is equal to 0. So 0.4 times FBE plus 0.65 times FCD is equal to 0.32 times W. And this will be your equation number 1. Now from our observation, the wire CD will yield. So what we are going to do, we will find this force in CD due to yielding will be equal to yield stress into the area. So yield stress is given as 530 megapascal. So 530 into 10 to the power 6 multiplied by area. Since it is circular, so pi by 4 into D, which is 0.04 meter, and it's square. That will give you FCD. So when you calculate this, FCD will be equal to 6.660 kilonewton. Now you have this value of FCD. So I will draw, let this was the initial beam, clear? So this is your point A, this is your point B, this is your point C, and this is your point D, G. So due to this load, the beam will deflect like this. So this B point will comes toward new point, which will be B dash. C point will move toward new point, which is C dash. So you can see we have the distance between A and B is given as 0.4 meter. From B to C, it is 0.250 meter. And from C to G, it is 0.150 meter. Clear? So we have, now you can see we have here, we will take two similar right angle triangle. One is this one, and another one is this one. So distance between B and B dash will be equal to delta B E, and from C to C dash it is delta CD. So by using this distance will be delta G. So by using similar triangle E, this is the triangle E B B dash and triangle AC C dash. So the ratio of their sides will remain same. So if we take delta BE divide by 0.4. So what I'm going to do is that I take this side and divide by this. The ratio of these two sides will give you delta BE divided by 0.4. And it will be equal to, if you take this right angle triangle, clear? So delta CD divided by 0.65. Delta CD divided by 0.65. So from here, we will get delta CD will be equal to 1.625 times delta BC. Now we know that change in length is equal to force into length divided by A into E. So we will write this delta as FCD into LCD divided by area into E is equal to 1.625 times del BC will be equal to FBC into LBC divided by area into E. So again, you can see both lengths LCD and BE both are 800. So it will cut with this, clear? Similarly, area will be same and modulus of elasticity is same. So what we will get is that FCD is equal to 1.625 times FBC. Clear? Now you have this equation. Let this equation is equation number 3. So put equation 3 in equation, put the value of this, let this is your equation number 2. So put equation 2 in equation number 3. So when you put the value of FCD, so FBC will be equal to FCD divided by 1.625. So 6.660 divided by 1.25. 1.625 will give you FBC. So FBC will be equal to 4.009 kilonewton. And let this is your equation number 4. Now put the value of equation 2 and 4 in equation number 1. This is your equation number 1. So putting equation 2 and equation 4 in equation 1. So how we will put is that 0.4 times 0.4 times FBE. Okay, FBE. So this is delta BE. Okay, so this is BE, not this is same as this is not BC, this is BE. Clear, BE. So delta BE. So 0.4 FBE, so 4.009 plus 0.65 times FCD. So FCD is 6.660 is equal to 0.32 W. So from here, what we will get, W will be equal to 18.7 kilonewton per meter. So this is the value of distributed load for one wire to yield. Clear? Now we'll move toward our second part, and in second part, both wires yield. So if both wires yield, so FBE will be equal to FCD, and that will be yield stress into area. So what is the yield stress? That is 530 into 10 to the power 6 multiplied by area. So area of wire is pi by 4 into 0.004 square. So it will give you FBE is equal to FCD, and that will be equal to 6.660 kilonewton. Now put FBE and FCD in equation 1. Equation 1 is this one. Clear? This one is the equation 1. So when you put it, you will get W will be equal to 21.9 kilonewton per meter. And this is the value of distributed load for both wires to yield. And that is all about this problem 4-100. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-95 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the 10 millimeter diameter shank of steel bolt has a bronze sleeve bonded to it. The outer diameter of this sleeve is 20 millimeter. If yield stress for steel is 640 megapascal and for the bronze, this is 520 megapascal, determine the largest possible value of P that can be applied to the bolt. Assume the material is to be perfectly plastic. Elasticity of steel is 200 gigapascal, and for bronze it is 100 megapascal. So you can see this is bolt, clear, having diameter 10 millimeter, and that is sleeve, bronze sleeve, that is made up of bronze, that is bonded to it, having outer diameter 20 millimeter. So diameter of bolt is 10 millimeter, in meter it is 0.01. The outer diameter of sleeve is 20 millimeter, which is 0.02 meter, and inner diameter is same as for bolt. Sleeve is made up of bronze. Yield stress of for steel is 640, while yield stress for bronze is 520 megapascal, and their modulus of elasticities are mentioned. So you have to determine the largest possible value of P that can be applied to the bolt. And how we will find this? So let's start with the solution. So first step is that, what if I cut the bolt over here or any length and draw the free body diagram? So let me draw it, that this is the head of this bolt, clear, and this is the sleeve. This is the sleeve. Okay, and this is the dotted line is the diameter of this bolt. So when I cut it, so you can see at the top we have a load P, which we are going to find, clear, and you can see that this load is taken, some of this portion of this load is taken by this bolt, which is represented as PB, clear, PB, and some of this load is taken by the shank, so that is PS. So total load P will be equal to PB plus PS. So how we'll find this? By using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and force upward is taken as positive. So I can write P minus PB minus PS is equal to 0, or you can also write it that P is equal to PB plus PS. Clear? Now how we'll find this PB and PS, and we are interested to find out the largest load. So I will write a statement that the largest possible P can be applied when you consider when P causes both bolt and sleeve to yield. That is the maximum load P that can be applied. So how we'll find this PB? So we know that yield stress for the steel is equal to load taken by the bolt divided by area of bolt. Clear? So from here, this PB will be equal to yield stress for this steel multiplied by area of bolt. So you can see 640 megapascal is the yield stress for steel. So 640 multiplied by 10 will be in pascal multiplied by area of bolt. Diameter is given as 10 millimeter, which is 0.01 millimeter. So area of bolt is pi by 4 d square, db square. So db is 0.01 square. That will give you PB. This PB will be the load that will cause the yielding in steel rod or steel bolt, and when you calculate it, you will get 50.265 kilonewton. Now we'll find the PS of sleeve. So we have yield strength for bronze that will be equal to P of brass. Oh, sorry, this is P of steel. PS. This is PS because this is the load taken by the steel. Now P of brass divided by area of brass, and similarly this will be AS, area of steel. So kindly make this correction. Okay, so from here, load taken by brass sleeve will be equal to yield strength of this brass multiplied by area of this brass. So the brass yield stress is 520 megapascal, so 520 multiplied by 10 to the power 6, and this sleeve having outer and inner diameter, so it will be equal to pi by 4. Outer diameter is 0.02 square minus inner diameter is 0.01, and the formula is pi by 4 d outer square minus d inner square. Now when you calculate it, the load taken by this brass sleeve will be equal to 122.52 kilonewton. As we know that we are interested to find of P, and we know that P is equal to PB plus P of steel, which we have written over here, clear? So put the value 50.265 is the value of steel, load taken by this steel rod or bolt, plus P bronze, which is 122.52 kilonewton. So when you add them both, so you will get 173 kilonewton. So this is the amount of, the maximum amount of load P that can be applied on this steel bolt having bronze sleeve bonded to it. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon for getting the upcoming videos. And if you have any question, you can ask me in comment section. Thank you for watching and keep supporting me like this. Welcome back. Problem 4-98. This problem is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the bar has a cross-sectional area of 0.5 square inch and is made of material that has stress strain diagram that can be approximated by two line segments shown. Determine the elongation of bar due to the applied loading. So you can see this is the bar where this at point C we have 5 kips load and at point B we have 8 kips load. And the stress strain diagram for this bar is given by two lines. So you have to determine the total elongation of this bar AC. So let's start with the solution. So as we know that total elongation in this bar will be equal to elongation in bar AB plus elongation in bar BC. Here you can see that we know that elongation or change in length is equal to PL divided by AE. So we do not know the material. It is not given. So we cannot apply this equation. So what we will do is that in this video, I will show you how to solve this problem. So first step is that what we will do is that if you cut this member BC, so for member BC or for segment BC, what if I cut it and draw the free body diagram? So this is member BC. At this we have 5 kips load, clear? And in order to balance it, we will having this load that this is PBC. So by using equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So PBC, which will be minus plus 5, is equal to 0. So from here we will get this PBC will be equal to 5 kip. Now you have this PBC. So what we will do is that we will find the average normal stress. So average normal stress in segment BC will be sigma BC is equal to PBC divided by area. So you have PBC is 5 and area of this bar is given as 0.5. So when you solve this, you will get 10 KSI. So stress in segment BC is equal to 10 KSI. Now what we will do is that we will find the stress in for segment AB. So I will write for segment AB. So what if I cut the segment AB and draw the free body diagram over here? So it will be like this. This is your point C where you have 5 kips load, clear? And this is your point B where you have a load of 8 kips. So in order to balance it, we should have a force toward left side, and this force will be equal to PAB. So how you will find PAB? By using the same equation, sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So PAB is in negative direction. So PAB plus 8 plus 5 is equal to 0. So from here you will get this PAB will be equal to 13 kip. Now you have this PAB. So what we are going to do is that we will find the average normal stress for PAB, that will be equal to PAB divided by area. So PAB is 13 divided by 0.5, and that will give you 26 KSI. So average normal stress in portion AB is 26 KSI. Okay, now we'll find the strain in segment BC. So how we'll find the strain in segment BC? So if you see that stress, we know that stress is equal to strain into E, clear? and E is equal to stress divided by strain. So we will take this ratio stress divided by strain. So for segment BC, we have strain sigma BC. If you take it and divide by, let me write it, we know that stress over strain. So for sigma BC over epsilon BC, if I take it, this will be equal to 10 divided by epsilon BC. And what if I take the ratio at this point? This is 20 sigma, and over for this 20 sigma, we have epsilon is 0.01. So we will take the ratio that sigma 10 divided by epsilon BC will be equal to 20 divided by 0.001. Let me explain again. You can see that this sigma BC is 10 KSI, that will be in this line. So if I take like this is 10, clear? So at 10, we will have some strain. So if the ratio of stress over strain at this point to the ratio of stress over strain to this point will be same. So what I have written is 10 divided by epsilon BC is equal to 20 divided by 0.001. So from here, we will get strain BC will be equal to 20 divided by 0.001. Strain will be equal to, sorry, let me correct it. It will be equal to 0.001 multiplied by 10 divided by 20. And when you solve this, you will get strain in BC will be equal to 0.00050. And it will be either unitless or inch by inch. So this is strain in BC. Now what we will do is that we will find the strain for portion AB. So what we will do is that you can see the stress is sigma AB, clear? So here, this is in this line. You can see this will be in, let me choose another color. This will lie in another line, in this line. So you can see 26. So 26 will be either somewhere here. Let this is 26. So if I take horizontal line, so at this point we will have strain will be epsilon AB. So what if I take the difference of these two stresses? For example, 26 minus 20 divided by epsilon AB minus 0.01. Let me write it. So you can see 26 minus 20 over epsilon AB minus 0.01. That will be equal to this 40 minus 20, this 20, clear? So 40 minus 20 divided by, at 40 we have strain 0.021 and at 20 we have 0.01. So 0.021 minus 0.001. So from here, when you solve this, you will get strain in portion AB will be equal to 0.0070 inch by inch, or it will be a dimensionless quantity. Now you have strain in BC and you have strain in AB. So we will move toward elongation. I will write elongation. So we know that change in length is equal to, strain is equal to change in length divided by original length. So for segment BC, this strain, this change in length will be equal to change in length of BC will be equal to strain in BC into length of BC. So what is strain in BC? You can see that is this one, 0.00050 multiplied by length of BC. So length of BC is 2 feet. So 2 and 1, we convert this feet into inch. So I will multiply it with 12. Okay, so when you multiply, it will give you 0.0120 inch. So this will be the change in length of BC, 0.0120 inch. Similarly, we will find for segment AB, So change in length of AB is equal to strain in AB multiplied by length of AB. So strain in AB is 0.0070 multiplied by length of AB. You can see this is 5 feet. So 5, and when you convert this feet into inch, so because 1 inch is equal to 1 feet is equal to 12 inch. So when you multiply it, you will get 0.420 inch. This will be change in length in AB. Now total elongation or total change in length will be equal to change in length AB plus change in length BC. So 0.420 is change in length of AB plus 0.0120 in length BC. So when you calculate it, you will get total change in length will be equal to 0.3432 inch. So due to the applied loading, total change in length is 0.432 inch. And that was all about this problem 4-98. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-93 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the maximum normal stress developed in the bar when it is subjected to tension of 8 kilonewton. So this is the bar you can see which is subjected to axial load of 8 kilonewton. There is a hole in this bar as well as in fillet. So due to this hole and this fillet, there will be a maximum stress at this portion, which is called stress concentration. So we have to determine that maximum normal stress developed in this load. So let's start with the solution. So we know that maximum stress is equal to K into sigma average, where K is known as stress concentration factor. And we will find this K for fillet as well as for hole. So starting from fillet, so at fillet, we will find this K. But before finding this K, we will find some values, which is R by H and W by H. So we will find what is W, what is R, what is H for this shape that is given in the rod. So you can see W is this one, which is the height, and that is 60 millimeter. So 60 millimeter. R is the radius of fillet. You can see R is this one. So that is 15 millimeter. And H is this height, which you can see that is given as this height here, and this is 30 millimeter. So 30 millimeter. Now you have this value. You have to find, use figure 4-23, that is for fillet, and you have to find R by H and W by H. So first we will find R by H and W by H. So what is R by H? R is 15 and H is 30. That will give you 0.5, and W by H is 60 divided by 30. That will give you 2. Now R by H is 0.5, which you can see is this point. If you draw a vertical line from this point, that will intersect these curves above. And we will locate W by 2. So W by H is 2. So you can see this is the curve which is intersecting at this point. So if you draw a horizontal line, so you will get the value of K is 1.4. You can see this on y-axis, this is K. So I will write K is equal to 1.4. Now you will use this equation, sigma max is equal to K into sigma average. So what is K? K is 1.4, and sigma average is load per unit area. So this is the load and this is the cross-sectional area. So load is 8 kilonewton. So I will write 8 multiplied by 10 to the power 3 divided by area. So this height is 30 millimeter, which in meter is 0.03 meter, and thickness is 5 millimeter, which is 0.005 meter. So I will write 0.03 multiplied by 0.005. Clear? And when you solve this, you will get maximum stress due to this fillets comes out to be 74.7 megapascal. Now we will move toward hole, and we will find K for hole. So at hole. So for hole, we will need 2R by W. So what is 2R and what is W? So 2R, you can see this is the hole of diameter, which is 12 millimeter. So 12 divided by W is this height of maximum portion which is carrying this hole, that is 60. So 12 divided by 60 will give you 0.2. Clear? Now look at the 0.2. So 0.2 is this point. So from this point, draw vertical line. It will intersect this curve. So from point of intersection, you can just move it over here. So this is 2.4, 2.45. This is 2.5. Clear? So this value is 2.45. So K will be equal to 2.45. Now for hole, we know that maximum stress is equal to stress concentration factor into sigma average. So 2.45 into load, which is 8 into 10 to the power, axial load 8 into 10 to the power 3 Newton. And you can see that this bar is carrying hole. So for area, we will take 60, which is 0.06 meter, minus diameter of hole, which is 0.12, into the thickness, which is 0.005. Clear? Because this hole is not offering any resistance to this axial loading, so thereby we subtract it from the net cross-sectional area. So I will write 0.06 minus the diameter of hole, which is 0.012, into thickness is 0.005. And when you calculate it, you will get maximum stress in hole, or on the side of hole, will be equal to 81.7 megapascal. Now this is the stress, maximum stress that is generated due to hole, and this is the maximum stress generated due to this fillet. So in question, we have been asked, determine the maximum normal stress developed in the bar. So among these two, or between these two, we will choose the maximum stress generated in bar is 81.7 megapascal. And that is the answer of our this question. And that was all about this problem 4-93. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel are requested to subscribe my channel and hit the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. And if you have any question, you can ask me in comment section. Thank you for watching and supporting me.